All right, welcome back. Today we're going to dive into a really fascinating corner of machine learning. It's a place where the computer basically plays detective. Imagine you give it a box full of clues, but no case file, no instructions. We're talking about unsupervised learning, which is really the art of finding order in pure chaos. So picture this. Someone hands you this massive, jumbled pile of data. It could be anything: customer purchase histories, a million social media posts, maybe even genetic information. But here's the catch. There are no labels, no categories, no instructions at all. It's just raw, chaotic information. So where do you even start? And that is the multi-million-dollar question, isn't it? It's kind of like walking into a library where every single book has been just thrown onto the floor. And it's your job to create the sections, fiction, nonfiction, science, history, but you're not allowed to read any of the titles. And that is the exact puzzle that unsupervised learning is built to solve. Okay, so here's our game plan for today. We're going to start with a really clear definition of what unsupervised learning even is. Then we'll roll up our sleeves and walk through a classic algorithm, it's called k-means, just to see how it works from the inside out. From there, we'll check out a more flexible method, hierarchical clustering, before kind of zooming out to see what other powerful tools are in the old clustering toolbox. So let's break it down. What exactly is this stuff we're talking about? Well, at its core, unsupervised learning really boils down to one key idea. The absolute most important words here are unlabeled data. Unlike other types of machine learning where you're constantly telling the algorithm, hey, this is a cat, this is a dog, here, you just give it a giant pile of pictures and say, you figure it out. The algorithm's entire job is to just look at all the data and find its own natural groupings, its own patterns, all by itself. Okay, so one of the most popular ways to actually do this is with an algorithm called k-means clustering. It is a total workhorse in the field, and it's a fantastic way for us to really get the core logic of how you find groups in data. At its heart, k-means is really all about segmentation. I mean, think about a company like Netflix trying to group viewers with similar tastes so it can recommend new shows. Or maybe a biologist who's grouping cells based on their genetic markers. That's the power of k-means. It takes a really messy data set and just carves it up into these distinct, similar groups that we call clusters. And the process itself is surprisingly intuitive. It really just follows these 4 steps. First off, you decide how many clusters you want. We call that K. And you just randomly place K starting points, which we call centroids. Then, for step 2, you assign every single data point to whichever centroid it's closest to. After that, you update the centroids by moving them right into the middle of their new little group. And finally, you just do it all over again. You repeat the assignment and update steps over and over and over until nothing changes anymore. Let's see it in action. Okay, so on the slide here, we've got our super simple data set. Just 5 points, A, B, C, D, and E, and each one has 2 coordinates. Just imagine these plotted on a basic graph. Our goal? We want to split these 5 points into 2 separate groups. So our K value is 2. Simple as that. All right, for step 1, initialization, let's just make it easy and pick 2 of our actual data points to be our starting centroids, point A and point B. Now for step 2, the assignment part, we calculate the straight line distance from every single point to each of our 2 centroids. And as you can see in the table, point C, well, it's closer to A. Point D is also closer to A, and point E is actually closer to B. So just like that, we have our first 2 clusters. Cluster 1 is A, C, and D, and cluster 2 is B and E. Okay, now this is the clever part. Step 3, the update. Remember, our initial centroids were just random guesses. So to find a better center for each cluster, we just take the average of all the points inside it. So for cluster 1, the average of points A, C, and D gives us a brand new centroid at coordinate 2, 2. And for cluster 2, the average of B and E gives us a new one at 6, 2.5. And here's where the magic really happens. We'd normally take these new, improved centroids and repeat the whole assignment process again. But in our simple case, something interesting happens. The clusters don't change. The points are still closest to the same new centroids. And when nothing changes, well, that's it. The algorithm is done. It's found its solution. We say that it has converged. But this whole thing raises a couple of big questions, right? First, how do we even know if our clusters are any good? And second, how did we know to pick k equals 2 in the first place? Well, for the first question, we use a score called inertia. You can think of it like a measure of tidiness. It tells you how tight and compact your clusters are. Lower inertia is better. For the second question, we use something called the elbow method. We just calculate the inertia for one cluster, then two, then three, and so on. When we plot those results, we look for a bend, like an elbow in the graph. And that elbow point, that's usually the sweet spot, the best number of clusters for our data. Now, k-means is powerful, for sure, but it has one big limitation. We had to decide on k, the number of clusters, right at the beginning. But what if you don't know the right number? Or what if the groups are kind of nested inside each other, almost like a family tree? Well, that's where a different method called hierarchical clustering really shines. Now, this method comes in two main flavors. The most common one is called agglomerative, which is a bottom-up approach. You start by treating every single data point as its own tiny little cluster. Then you find the two closest clusters and merge them into one. And you just keep doing that, merging the next closest pair and the next until you're left with one giant cluster that contains everything. The other approach, called divisive, does the exact opposite. It starts with one big group and just keeps splitting it apart. So a key challenge here is, how do you measure the distance between two clusters once they have more than one point in them? I mean, do you measure from the closest points in each cluster? That's called single linkage. Or do you measure from the 2 points that are farthest apart? That's complete linkage. Or maybe you take the average of all the possible distances. That's average linkage. And believe me, the method you choose can completely change the final structure you end up with. But the final output is what makes this method so cool. Instead of just getting a final list of clusters, you get this beautiful tree diagram called a dendrogram. It gives you the full story, the entire hierarchy of how all the data was merged together step by step. This means you can just look at the structure and decide later on where you want to cut the tree to get the number of groups that makes the most sense to you. Okay, so k-means and hierarchical clustering. They're absolutely foundational, but they are just the beginning. The world of clustering is huge, and it is filled with all kinds of specialized tools for different problems. Just think of these as different tools in a data scientist's toolbox. For instance, what if your clusters aren't nice little circles, but they're weird, long, snaking shapes? And what about data points that just don't seem to belong anywhere? For that, you'd use something called dbScan. Or what if you want to let a single data point belong to multiple groups at the same time? That's what Gaussian mixture models are for. And there are even super specialized tools, like spectral clustering for things like social networks, or BIRCH for when you're working with absolutely massive data sets. The key takeaway is that for every unique data puzzle, there's probably a unique clustering tool designed to solve it. So the next time you get a movie recommendation, or you see a weirdly specific ad, or read about new genetic research, just remember these algorithms are working silently in the background. They're finding patterns, they're creating groups, and they are assigning labels that you will never ever see. It kind of makes you wonder, right? Based on your own data trail, what hidden cluster, what invisible group do you belong to?
Welcome back to the deep dive. Today, we are really handing you the blueprint for, well, one of the most essential concepts in modern analytics. It's about how machines can find this profound hidden structure when, no human has told them what exactly to look for.
Right, when there are no labels.
Exactly. So if your goal is to quickly get a handle on the complex world of data segmentation, taxonomy, maybe unsupervised insight, you are definitely in the right place.
We're diving deep into clustering algorithms, unsupervised learning.
And that's the core challenge, isn't it? I mean, most people think machine learning, they picture supervised tasks.
Sure, like classifying emails or predicting stock prices.
Yeah.
You have labeled historical data. You know the answers you're aiming for.
But unsupervised learning, it feels like a leap of faith sometimes. The algorithm gets data with absolutely no predefined outputs or categories.
Correct. There are no right answers provided upfront.
So the system isn't trying to match known answers. It's more like it's dropped into this huge pile of raw, maybe chaotic data and just told, find the natural groups, go discover the structure in this chaos.
Precisely. Its whole mission, really, is to discover hidden patterns, underlying structures, maybe relationships we didn't even know existed, all on its own.
Structure discovery without a map. I like that.
That's the essence of it.
Okay, so our mission today is to equip you, the listener, with the essential toolkit for this kind of discovery. We want to master the mechanics, and the pitfalls too, of the two biggest algorithms, k-means and hierarchical clustering.
And then we should probably survey some of the more advanced, specialized algorithms you might need when Real-world data shapes get a bit weird.
Definitely. Let's start by unpacking the geometry, I guess, of k-means. So k-means, it feels like the foundational workhorse here. It's efficient. It scales pretty well.
And it's often the first place people start for grouping similar data points, segmentation tasks.
Right. The concept seems simple enough. You just specify the number of groups, k, and the algorithm finds their centers, the centroids.
The actual steps are pretty intuitive, too. You've got initialization, assignment, update, and repeat.
Okay, walk us through that. Initialization.
You basically pick k starting points, kind of randomly at first. These are your initial guesses for the cluster centers.
Then assignment.
You take every single data point and assign it to whichever of those starting centroids is closest, usually using standard distance.
Okay, distance calculation. Then update.
Right. Now that you have initial groups, you recalculate the true center, the mean, of all the points within each group. That becomes your new centroid.
And repeat. You just keep doing that, assigning, updating.
Exactly. You iterate those two steps, assignment and update, until things stabilize.
But hang on, relying on random initial points, that sounds like where the trouble could start, right? If your first guesses for the centroids are just, well, terrible, couldn't your whole analysis end up way off?
Precisely. That is probably the biggest structural weakness of the classic k-means approach. The algorithm will converge. It's guaranteed to stop eventually.
Okay.
But it's only guaranteed to converge to what we call a local optimum. It might not find the absolute best possible grouping for your data overall.
So a bad random start can basically trap the algorithm in a kind of mediocre grouping, producing clusters that aren't really the best fit.
That's exactly it. Suboptimal clusters.
So we obviously need a smarter way to kick things off than just, throwing darts at the data map. What's the standard fix for these bad random starts?
Well, that's where k-means plus plus comes into play. It's a smarter initialization strategy.
K-means plus plus. Okay, how's it different?
Instead of picking all k centroids completely randomly right at the start, k-means plus plus selects them more deliberately. It picks the first one randomly.
Okay.
But then, for each subsequent centroid, it chooses a new point that's far away from the centroids already chosen. It uses a probability distribution based on distance.
So it tries to spread the initial guesses out.
Exactly. It prioritizes picking initial centers that are distant from each other. And that dramatically reduces the chance of getting stuck in one of those poor local optimums you mentioned.
That makes sense. It's a small tweak, but sounds powerful.
It really is.
Yeah.
A key thing for practical implementation.
Now let's talk about the tool it uses for that assignment step. Distance. K-means typically relies on Euclidean distance.
Right, the straight line distance.
Yeah.
Like using a ruler in 2D or 3D space. Simple and intuitive.
But when does that classic method start to break down? Is it always the best choice?
Well, Euclidean distance works great when you have relatively low dimensional data, maybe 2, 3, 4 features per data point.
Okay.
But if you're trying to cluster something like, say, documents based on hundreds or thousands of word frequencies, you run smack into the infamous curse of dimensionality.
Yes, the curse. Which, simply put, means that when you have tons of dimensions, everything starts to look equally far away from everything else. Is that the gist?
That's the core problem. Yeah. The whole concept of nearest neighbor or closeness starts to lose its meaning because distances become less discriminative.
So if you're clustering really high-dimensional stuff like text data or maybe genetic sequences, Euclidean might not be the way to go.
Often, no.
Yeah.
You usually need to consider other metrics, things like cosine distance, which looks at the angle or direction between vectors rather than just magnitude. Or maybe Manhattan distance, which can be more robust if you have outliers.
Interesting. So choosing the right distance measure might actually be more critical than picking the clustering algorithm itself sometimes.
In high dimensions, absolutely. It's a crucial decision.
Okay, so let's say we've run k-means, maybe used k-means plus plus to start, picked a good distance metric, the centroids have stabilized. Now we face that fundamental challenge of unsupervised learning. How do we actually know if the groups we found are any good?
Right. We don't have ground truth labels to compare against, like in supervised learning.
So no accuracy score.
No simple accuracy score, no. We have to rely on internal validation. We need ways to measure the quality based purely on the clusters themselves and the data points within them.
How do we do that? What are we looking for?
We generally focus on two key aspects: cluster tightness, or cohesion, and cluster separation. How compact are the groups, and how distinct are they from each other?
Okay, tightness first. We use inertia for that, right?
Correct. Inertia is technically the sum of the square distances of all the points within a cluster from that cluster's own centroid.
So low inertia means points are tightly packed around their center. They're cohesive.
Exactly. A lower inertia value generally indicates denser, tighter clusters.
Okay, that covers tightness. What about separation, making sure the groups are distinct?
For that, a common metric is the Dunn index.
Dunn index. How does that work?
It basically looks at the ratio between the minimum distance between any two clusters and the maximum distance within any single cluster.
So it considers both how far apart the clusters are and how spread out they are internally.
Precisely. You want a high Dunn index. That indicates that your clusters are both compact, small internal distance, and well separated, large distance between clusters. Tight and separate means high quality.
Got it. So inertia and Dunn index give us ways to measure quality, which brings us back to maybe the biggest practical headache with k-means. Choosing k, how many clusters should we even look for?
Yes. The eternal question.
Everyone hears about the elbow point method. You plot k versus inertia, and you look for that elbow bend in the graph.
Right. The idea is that adding more clusters beyond the elbow doesn't decrease the inertia significantly, diminishing returns.
But in practice, I found the elbow can be pretty subjective. Sometimes it looks more like a gentle curve or maybe a wrist. It's often really ambiguous.
Oh, it absolutely is ambiguous. There's a very common frustration. It's not always a sharp, obvious elbow.
So is there a better way, something less eyeballed?
Well, yeah. That's why practitioners often rely on a more sophisticated metric, one that kind of inherently combines both that tightness and separation idea, trying to bypass the elbow ambiguity. We're talking about the silhouette score.
Okay, silhouette score. Tell us about that. How does it give a clearer answer for K?
The silhouette score does something clever. It calculates a score for every single data point.
For each point, okay.
Yeah, and that score measures how similar that point is to its own cluster compared to how similar it is to the nearest neighboring cluster. It ranges from -1 to +1.
What do the scores mean?
A score close to +1 means the point is well inside its own cluster, far from others. It's well clustered.
Makes sense.
A score near 0 means the point is basically sitting right on the fence, on the boundary between two clusters. Ambiguous.
And negative.
A score close to -1 suggests the point might actually be in the wrong cluster altogether. It's closer, on average, to points in a different cluster.
I see. So how does this help choose K?
Instead of looking for that fuzzy elbow, you calculate the average silhouette score across all data points for different values of K. Let's say you tried K2, K3, K4, and so on.
And then?
You pick the value of K that gives you the highest average silhouette score. That K is generally considered the best choice because, on average, the points are most appropriately assigned to distinct, well-separated clusters.
Okay, so it gives a more statistically grounded answer by directly measuring that combined idea of tightness and separation for each point. Less ambiguity.
Exactly. It's a very useful metric in practice. Now, k-means is fantastic, as we said, a real workhorse. But it does have limitations. It tends to assume clusters are, well, roughly spherical and maybe equally sized.
Right. And real-world data, it rarely behaves that nicely, does it?
Not often, no. Which brings us to our second major algorithm, hierarchical clustering.
This is the one that doesn't just put things into separate bins, but actually organizes them into a meaningful linked tree-like structure.
Exactly. That tree structure is called a dendrogram, and it's incredibly powerful because it visualizes the relationships and the nested similarities within the data.
So it's really useful for things like creating formal taxonomies, like, biological classifications, or maybe mapping organizational structures.
Precisely. Because it explicitly identifies those deep hierarchical relationships.
Yeah.
It shows you how clusters merge together at different levels of similarity.
Now, I remember hearing about two main types, bottom-up and top-down.
That's right. The most commonly used approach is agglomerative hierarchical clustering. That's the bottom-up method.
Okay, bottom-up, how does that work?
You start really simple. Every single data point is its own tiny cluster.
1.1 cluster, got it.
Then you find the two clusters that are closest to each other, based on some distance measure, and you merge them into one new cluster.
Okay, merging the closest pair.
And you just keep doing that, iteratively merging the two closest clusters that remain, until eventually you're left with just one single giant cluster containing all the data points.
And the reverse is divisive clustering, top-down.
Correct. Divisive starts with everything in one big cluster and then recursively splits clusters into smaller ones. It's less common, though.
Right.
Agglomerative is generally the default people think of.
Okay, let's stick with agglomerative then, the bottom-up approach. The complexity seems to arise when you start merging groups of points, not just individual points. Say we've merged points A and B into cluster AB. How do we now define the distance from this new combined cluster AB to some other cluster, say cluster C?
Ah, yes. That is absolutely the crucial question, and it brings us to the concept of linkage.
Linkage, okay.
Linkage is the strategy, the rule you use to calculate the distance between two groups of points, not just two single points. Let me tell you, choosing the wrong linkage method can give you wildly different clustering results, even using the exact same data.
Really? So the linkage choice is critical. We usually hear about single, complete, and average linkage. What are the practical differences? Let's start with single linkage.
Okay. Single linkage is maybe the simplest. It defines the distance between two clusters as the minimum distance between any single point in the first cluster and any single point in the second cluster, the closest pair.
The shortest possible link between the two groups.
Exactly. Now, this approach tends to produce kind of loose, elongated clusters, and it's particularly notorious for something called the chaining effect.
Chaining, what's that?
Imagine you have two fairly dense groups of data points, but they're separated by a kind of thin string or bridge of scattered points connecting them.
Okay.
Single linkage will see that string as a valid path between the groups because the minimum distance between adjacent points along that string is always small. So it tends to merge clusters based purely on the proximity of their closest edges, which can lead to these long, stretched-out clusters that don't really reflect the underlying density or shape very well.
Ah, I see. It just follows the chain of close points,
Yeah.
which often isn't what you want.
Usually not, no.
Yeah.
So to combat that chaining effect, we often turn to complete linkage.
Okay. Complete linkage. How does that work?
It does the opposite. It uses the maximum distance between points in the two clusters. So the distance is defined by the 2 points, one from each cluster, that are furthest apart.
The longest possible link.
Right. And this forces the algorithm to find much more compact, sort of sphere-like clusters, because the distance calculation is now dominated by the most distant outliers in each group. It won't merge unless even the furthest points are reasonably close.
That makes sense. It avoids the chaining by focusing on the extremes.
Correct. And then finally, there's average linkage.
The middle ground.
Pretty much. Average linkage calculates the distance between two clusters as the average distance between all possible pairs of points, taking 1 point from each cluster.
So it considers all the points, not just the min or max distance.
Exactly. It tries to strike a balance between the extremes of single and complete linkage. It's often a good compromise.
So the choice of linkage fundamentally shapes that dendrogram tree we talked about. It's not just a picture, it's a direct result of how you decided to measure distance between merging groups.
Absolutely critical. Linkage matters.
Okay, so we've covered k-means and hierarchical clustering. They're sort of the rigid foundational methods. But as we hinted, they're really just the start, aren't they?
Definitely just the start.
If you're dealing with noisy data or maybe massive scale or really complex non-spherical shapes, you probably need to leave those fundamentals behind and reach for something more specialized.
Right. This is where data science gets really interesting, I think, because the choice of algorithm starts to dictate the shape of the insight you can even possibly find. Different tools uncover different kinds of structure.
Let's survey some of these specialized tools for the listener. Where should we start? Maybe with the algorithm that completely ditches the whole idea of a centroid, DBS-scan.
Ah, DBS-scan, yes. Density-based spatial clustering of applications with noise. It's kind of revolutionary because its superpower isn't distance to a center, it's density.
Density, how does that work?
Instead of calculating distances to centroids, DBS-scan defines clusters simply as areas where points are densely packed together, separated by regions that are relatively sparse.
So it finds dense neighborhoods.
Exactly. It looks for core points, points that have a minimum number of neighbors, min-PTs, within a certain radius, epsilon or epsilon. Clusters are formed by connecting these core points and the points reachable from them.
Which means it can find arbitrarily shaped clusters, like spirals or half-moons or maybe dense regions that look like galaxies, shapes that k-means would just completely mangle.
Absolutely. That's its great strength. It doesn't care about spherical assumptions. It just follows the density. And crucially, any point that isn't part of a dense region, that isn't reachable from a core point, it gets labeled as noise.
Ah, so it's also great for outlier detection, identifying weird stuff.
Perfect for it. Finding unusual credit card transactions, maybe weird network activity, anything that doesn't belong to a dense group can be flagged as noise or an outlier.
Okay, but what if the density isn't uniform? Like some clusters are way denser than others. Can DBSCAN handle that?
That can be a challenge for standard DBSCAN, choosing a single epsilon and min-Pete's value that works for all densities. That's where an extension called OPTSCS comes in.
OPTSCS.
Ordering points to identify the clustering structure. It's designed specifically to handle clusters of varying density more effectively. It doesn't just output fixed cluster labels like DBSCAN.
What does it do instead?
It creates a special ordering of the points based on their density relationships. And from this ordering, you can extract clusters that correspond to different density levels. It gives you more flexibility.
Interesting. Okay, let's switch gears and tackle that choosing K problem head on again. Is there an algorithm that just figures K out for us?
There is mean shift clustering.
Mean shift, how does that avoid needing K?
Mean shift works quite differently. It thinks in terms of density landscapes. Imagine your data points creating hills and valleys based on how dense they are. Mean shift tries to find the peaks or the modes of this density distribution.
So it climbs the hills.
Kind of, yeah. It starts with points and iteratively shifts them uphill towards the nearest area of higher density. Points that converge to the same peak belong to the same cluster.
And the key advantage?
It does not require the number of clusters K to be specified in advance. It automatically discovers how many significant density peaks, and therefore clusters, exist in the data.
How would you use that?
It's very widely used in things like image processing and computer vision. For example, segmenting an image by grouping pixels with similar colors. You don't know beforehand how many dominant clusters there are. Mean shift finds them.
Cool. Okay, now let's step away from these sort of hard geometric or density ideas and move into the realm of probability. You mentioned Gaussian mixture models, or GMMs.
Right. GMMs take a probabilistic approach. Instead of assuming a cluster is just a sphere defined by a single center point, like he means.
It assumes
that the data points belonging to a cluster are generated from a Gaussian or normal distribution. Each cluster has its own mean and covariance matrix defining its shape, which can be elliptical, not just spherical.
So more flexible shapes. What's the real power here?
The real power is that GMMs introduce the concept of soft clustering.
Soft clustering, as opposed to the hard assignment in K-means, where a point is either in cluster 1 or R cluster 2.
Exactly. Soft clustering provides a probability that a given data point belongs to each of the clusters.
So a point could be like 70% likely to be in cluster A and 30% likely to be in cluster B.
Precisely. Think about customer segmentation. Maybe a customer isn't just an early adopter or a budget shopper. Maybe they have characteristics of both. GMMs can capture that kind of nuanced reality, that uncertainty.
How does it figure out those probabilities?
It uses a powerful iterative algorithm called expectation maximization, or EM. It alternates between estimating the probabilities, expectation step, and updating the cluster parameters based on those probabilities, maximization step. It's much more flexible than rigid geometric methods.
Okay, probabilistic clustering with GMMs. Now, what about really complex shapes? Things that are topologically connected, maybe, but geometrically separate, like, I don't know, two intertwined spirals.
For those really non-convex, tricky shapes, you often need to bring in graph theory. You need spectral clustering.
Spectral clustering sounds advanced.
It is, but it's very powerful for these non-convex situations. It doesn't primarily look at the raw distances between points in the original space.
What does it look at instead?
It transforms the clustering problem into a graph problem. First, it builds a similarity matrix, which is basically a graph where your data points are the nodes, and the weight of the edge between two nodes represents how similar those 2 points are, often using something like a Gaussian kernel.
Okay, so it turns the data into a network map based on similarity. Then what?
Then it analyzes the structure of this graph, using linear algebra specifically. The eigenvalues and eigenvectors of a matrix derived from that similarity graph, often the Laplacian matrix.
Eigen. Okay, math gets serious here. Yeah. What does that achieve?
It essentially uses this spectral analysis to project the data into a new, lower dimensional space, where the clusters, even the weirdly shaped ones, become much more easily separable, often linearly separable.
So it finds a new perspective where K-means can actually work effectively.
That's a great way to think about it, yes. It separates groups that are connected by the underlying structure or manifold of the data, even if they look far apart or tangled in the original Euclidean space.
So if you're analyzing, say, complex social networks, or maybe some highly convoluted data from physics or biology, spectral clustering might be the tool.
Often it's the superior choice for those kinds of complex connectivity patterns.
Okay, one last challenge. Sheer scale. What if your data set is just enormous, too big to fit into memory for some of these calculations?
Right, big data clustering. For that, you'd look at something like BRCH. BIRCH, balanced, iterative reducing and clustering using hierarchies. BIRCH is specifically designed for very large data sets.
How does it manage the scale?
It overcomes memory limitations by not storing all the data points directly. Instead, it creates a highly compact in-memory summary of the data as it reads it. The summary is stored in a special tree structure called a clustering feature. CF tree.
A CF tree.
Yeah, the nodes in this tree store condensed information about subgroups of points, like their count, linear sum, and sum of squares. BIRCH builds this tree incrementally as it scans the data.
And then it clusters the summary, not the raw data.
Essentially, yes. It can perform clustering directly on the leaf nodes of the CF tree, which represent a much smaller summary of the original massive data set. This makes it really efficient and excellent for situations like clustering streaming data or handling petabyte-scale analysis.
Wow. Okay. We have really covered some ground here. We went from defining that core challenge of unlabeled data to mastering the rigid geometry and those crucial initialization fixes for k-means.
Like k-means ++.
Right. Then navigating the whole hierarchy and the critical linkage choices in hierarchical clustering and dendrograms.
Single, complete, average.
Yeah. And finally, hitting this amazing toolkit of specialized algorithms like DBSCAN for density, GMMs for probability and soft clustering, spectral for those really complex shapes, and BIRCH for sheer scale.
It's quite a journey through different ways of finding structure. And these techniques, they're really the key, aren't they, to turning what looks like chaos into actionable structure.
They provide the frameworks for segmentation, for taxonomy, the insights needed in basically every field, from market research to physics.
They literally help find the insights that were previously just hidden, buried under the sheer volume of raw, unlabeled data.
Okay, so here's a final thought for you, the listener, to maybe mull over as you think about how to apply this knowledge. If these sophisticated algorithms are constantly out there searching for hidden, unlabeled structure, using metrics like the silhouette score, leveraging the nuance of things like the EM algorithm and GMMs, how many deeply structural, really significant relationships might currently exist in these vast corporate or scientific or maybe even political data sets that just haven't been quantified or labeled yet?
Yeah.
Simply because maybe the right specialized clustering algorithm hasn't been run.
A fascinating question. What hidden structures, what unknown clusters are just waiting there to be uncovered in your own area of interest, in your data?
That really is the profound potential of unsupervised learning.
It truly is.
Go deep. We'll see you next time.